All right, today we're going to talk about the strategy pattern. Okay, the intent of the strategy pattern is to define a family of algorithms, encapsulate each one, and make them interchangeable. So we use the strategy pattern when we know there are many ways of accomplishing the same behavior. So rather than include all the different ways in a single class, what we'll do is we'll separate out the different ways and plug them in when necessary. So for example, when one example of this is if we were trying to write a program to, say, find the area under a curve. Okay, so let's say this is some function here, like x squared, and we want to find the area from this point to this point. Well, there's actually many different ways we could do this. We could, we could maybe create a triangle and somehow estimate the area under the curve that way. We could maybe come up with a bunch of circles, right? Take the area of each one of those and see how many circles we can fit in there. Or maybe probably the best known one is to make a bunch of boxes and find the area of each one of the boxes and sum up those little areas. So really finding the area under the curve, that's pretty much the same in each one of those cases I just talked about. The part that's different is, well, what was the shape that we drew? Was it a circle? Was it a triangle? Was it boxes? Okay, so the idea of the strategy is to pull those different ways of essentially doing the same thing out and making them reusable. Another example might be if we were trying to find the either a square root of a number or all the numbers that are prime in a certain range. Right? So if we wanted to find the square root of 100, one thing we could do is just kind of start in the middle and guess, right? Square that, and we'd see that's way too big. So maybe then limit our range to just here, and maybe guess again, and we'll say, oh, that if we square that, that's way too big. Okay, but that's not the only way we could find a square root. We could also maybe create several different threads that look in different areas of this number line to see, is the square root somewhere in here? And if so, we'll maybe break that into even smaller chunks and ignore all the other ones. Again, there's something common to this problem, and there's also something different, right? The different strategies or approaches of figuring out, in this case, the square root of a number. Okay, so the motivation. Many algorithms exist for performing the same behavior. Hardwiring all these algorithms into a class that needs some of the behaviors isn't desirable. Why? Well, the client code becomes more complex. The client, the people who are using your class, might be overwhelmed by all the different options they have and how something's implemented. So, the area under the curve problem, you might have a find area with boxes, find area with triangles, find area with circles. All those little methods just add complexity to the problem. It's difficult to add new algorithms later. So if the algorithms are hard-coded into this class, it's more difficult to add new algorithms later. If the algorithms are separated from the classes that use them, it's easy to plug in new algorithms as needed. Okay, again, so if somebody came up with a different shape, octagon, maybe there's a really clever way to take the area of an octagon and basically do the same thing, put all these octagons under the curve and sum up their areas. Well, it'd be easier to add that algorithm if we use this strategy pattern. See another one here. Different algorithms will be appropriate at different times. So if we load a class with many different algorithms, we have to maintain them, even if we're not using all of them right now. So in our early code, we may have accomplished some behavior with some code, but then later on we decide we're going to do something different. If we keep both implementations in the class, we really have to support and maintain both implementations, even if we're not going to use them. If we separate the algorithms out, we can very easily kind of ignore or not have to maintain old solutions. Okay, so here's a class diagram for the strategy pattern. And I often find that the class diagram in the structure section of a pattern to be really one of the most useful parts of the pattern. So when I think of patterns, I think of these little pictures of classes. This says there's going to be some application-specific context class that will hold a reference to a generic strategy object. And the strategy is so generic, it's an interface. There's not actually anything in the strategy interface except this one method, which we're using the generic operation as the method name. Okay, the reference will eventually point to a concrete strategy, but since a concrete strategy is a strategy through inheritance, the context reference can point to any concrete strategy. So yeah, the context in the context class, there will be a reference of type strategy, but it will really be pointing to either concrete strategy A or concrete strategy B. Okay, all strategies know how to perform some operation. Remember, patterns are very general. We discussed the problem very generally and the solution very generally. Okay, I'll show an example soon of how to apply this particular pattern to a very specific problem. Next, we have some participants. So let's go through each one of these classes. The context class, that's the one that contains a reference to a strategy object. And again, the type of the reference is going to be the generic strategy. The strategy interface declares the interface that's common to all strategies. Okay. And the concrete strategy implements an algorithm that uses the strategy interface. Okay, what are the consequences of using this class? Well, for related algorithms, you can factor out the commonalities, and only the strategies are different. So think of the area under the curve. We were basically building these shapes and finding their areas and summing their areas, but whether we used a square or a triangle or a circle, that was what was different. And then one can actually change strategies on the fly as the program is running. Okay, so let's look at an example. Okay, and let's imagine that we were going to implement this financial advisor application. So the financial advisor would like to see the value of a portfolio. So this will probably involve methods like getting the cost to purchase, getting the value of the portfolio, and getting the profit. Because most people are most interested in the profit or loss. So one might be tempted to create a class that looks like this. We might have a financial advisor class. And we might include these methods to get the cost to purchase. Maybe that returns a double. We might have a get value. Returns a double. And a get profit. Okay, so this is our class. It's called Financial Advisor. It has these methods. The problem is that the financial advisor might want to explore the value of the portfolio under different circumstances. Right? So when we talk about getting the value, we might want to consider a very optimistic future. So maybe take the current value of the market and increase it by some percentage. Or maybe a pessimistic future. Take the current value of the market and decrease it by some percentage. Or we might want to see, well, what is the value exactly today, right now? We'd have to go and get the current value of all the stocks. Or the financial advisor might want to play around with different sectors. So maybe the tech stocks would be, let's imagine the tech stocks were super high, but the blue chips were low. Okay, I think financial advisors like to play around with their models like this to see, well, what would happen if? Okay, the algorithm to determine the profit is the same in all of these cases. Right? So here's a financial advisor class with a get profit method. And basically what we do is we need to get the cost to purchase. We need to get the value for the portfolio. Of course, financial advisors always charge some fees. And we can just take the value minus the cost to purchase. That's the kind of the net value. And then you subtract the fees, and whatever's left, that's the profit. Okay. So getting the profit, it's really kind of the same in every case, where we have to get the cost to purchase, we have to get the fees. No matter what the circumstances are, that part of getting the profit is always the same. However, getting the value of the portfolio is different because the advisor wants to be able to experiment with different market conditions. So we wouldn't want to introduce additional methods to this class, right? Before we had just a single get profit. Your instincts might say, well, let's just add a get profit optimistic and get profit pessimistic and get profit today and get profit with changing sectors. Because really the only thing that would be different about these methods is how the value calculation is made. Everything else about calculating the profit is the same. We get the cost to purchase, we subtract the value, we subtract the fees, and that's the profit. So these four methods would basically be copy and paste of the original get profit, and then we would change just a little bit, one line, how we get the value for that portfolio. Okay, so from our motivation section, right, the person using the financial advisor class would have more complexity to deal with these additional methods. Because remember, the core calculation is really quite simple, but we're adding all of these methods that make it more complex to the person using the class. Okay, it's pretty painful to add new algorithms. You would have to open up the financial advisor class to add these new methods, and then keeping up all of our clients up to date with all of these different methods, right? Because there might be even many more experiments that financial advisors want to experiment with. Now we'd have to keep all of our clients up to date with those methods. Even those, a majority of our clients may not want all of those algorithms, or maybe they didn't pay for all those algorithms. Every advisor might also not use all of these methods, but like I said, we still have to support them because we're delivering them as part of this class, and they expect to be, updated. So there's basically a lot of work to keep this class up to date with methods that maybe some of our clients aren't even using. Okay, so instead what we should do is we should pull the commonalities out and let the strategy change. Okay, so what I think these classes should look like is something more like this, where we have our financial advisor class. And it has a reference to what I'm going to call a value strategy. Okay, and we'll see this. This is an interface. Okay, and the value strategy has a method called getValue. And then we'll have several concrete strategies. So for example, we'll have an optimistic strategy. We'll have a pessimistic strategy. We'll have a strategy for today. And we'll have a strategy for changing sectors. Again, this one means let's imagine tech sector stocks went high and agriculture stocks went low. These are the different sectors I'm talking about. Okay, so look at how this class diagram relates to the generic class diagram. Okay, so we had a context, that's our financial advisor. We have a generic strategy called the value strategy, and then we had several concrete strategies: optimistic, pessimistic, today, and change sector. This is very common in a pattern. The structure is a very general structure, and then we have to apply it to our particular problem. Okay, so let's look at some more code here. We'd start with this interface called value strategy that has a single method called getValue. Now, any class that implements this interface must provide an implementation for this method called getValue. But of course, the definition of an interface is it's filled with purely all abstract methods. Right? So we have no implementation, no data in an interface. It's kind of like a contract. Okay, then we start to define these actual strategies. So the optimistic class implements value strategy. And remember, what we're going to do with optimistic is take the current rates and increase them by some, get the current value of the market and increase it by some rate. So there's a constructor that takes a rate, right? And then we override getValue, where I left out the code, but we increase all stocks by whatever rate the user specified. And pessimistic is very similar to implements value strategy, but this time we have a decrease rate. And the way we get the value for the pessimistic strategy is we decrease all stocks by this percentage. And then the today strategy, again, implements value strategy, and to get the value, we go on the internet and get today's stock prices. And the change sectors strategy, again, we maybe we have some kind of GUI that prompt the financial advisor for the sectors and the relative change. Okay, each strategy was implemented differently. Okay, right? Each one of these optimistic, pessimistic, today, change sectors, the way we get the value was different for each one of these classes. Okay, but finding the profit is essentially the same for all. Okay, so let's look at our new financial advisor. Okay, now we have a reference to a value strategy. Remember, value strategy is that interface. So it can point to any object that implements the value strategy interface. Okay, the financial advisor maybe takes a value strategy in the constructor, and maybe the first thing we do is we store that strategy to use. And again, it can be any of the derived classes. Now, getting the profit, we just have a single method called getProfit, where getting the cost to purchase is the same regardless of the strategy. Getting the fees, that's the same regardless of the strategy. What's different, though, is the value. So here, instead of just calling getValue, we say, give me the strategy that this financial advisor points to, and we'll ask that strategy to get the value. Okay. And then we still do our simple calculation, value minus cost minus fees. That's how we determine our profit. Okay. Now let's look at a driver that might use this financial advisor and these different strategies. We can start by creating some different strategy objects. So optimistic says, what would happen if everything got 10% better than it was? Pessimistic says, let's decrease everything by 20%. Today is a strategy. Change sectors is a strategy. Okay. Then we create a new financial advisor object, and we pass in one of the strategies. Remember, that was in the constructor. This is just the first strategy. We'll see in a second that we can change strategies on the fly. Okay, so we're starting out with the optimistic strategy. And when we say f.getProfit, right, we're going to go to the financial advisor's getProfit method, And the current strategy is going to be that optimistic type. So when we get the value, we're going to increase the current values by 10%. Okay. Then we can change to a pessimistic strategy, right? Just by passing in a new strategy object. P is the pessimistic one. Okay, that's going to associate this strategy with the financial advisor. And now when we say f.getProfit, again, we're going to do the same thing each time, but the strategy now points to a different concrete object. So when we get the value, we're going to decrease the current stocks by 20%. Okay, then we can use today's strategy. Again, just change the strategy and call getProfit. And we can change whole sectors by, again, setting the strategy and calling getProfit. So strategy is nice in that we pull out the one part of an algorithm that changes or is likely to change, and then we keep the part of the algorithm that really is the same regardless of the different strategies. Okay, and this is a nice way to decompose this system and keep everything nice and simple. That's the strategy pattern.